Today I will present efficient preserving, privacy preserved processing of multimodal data for vehicular traffic analysis. Here's my outline. I'll probably first start with some introduction about the work, going through some background, and then I'll present the motivation, proposed methodology, followed by some evaluation and concluding remarks. So the need for the privacy is a crucial need these days, as we can see it mostly due to the popularity of placing lots of activities and information on third-party cloud that facilitates a lot of computation with efficient cost and timing. But unfortunately, this kind of outsourcing or releasing information most of the time is not complied with the required privacy measures that has to be in place, specifically due to the different concern that customers' activity can be exploited by unauthorized parties that finally may target them with ads or blackmailing, or some leaked topology of the networks of some organizations that sharing their network their logs or the other types of sensitive information to cloud can be compromised and lead to different types of attack like denial of service. And also, according to GDPR Article 28, providers cannot share tenants' data without protection while acquiring the service of the third party. So to this end, the problem of making these services privacy preserving and privacy friendly while ensuring the usability of the services is an important challenging problem that has attracted lots of researchers over the course of last 20 years. And the fact that what anonymization technique has to be applied so that we can enjoy both world of privacy and utility. One of the current state of the art metric of privacy is called differential privacy, which is considered as a privacy standard by providing plausible deniability in the output of different algorithms through mostly the filter of through mostly a noise filter that will be applied over the outcome of each query that has access to a data set. And the guarantee is something like, from the adversary perspective, we want to make sure that the output will not reveal presence or absence of one specific individual that can be seen here as two possible cases. And very technically, we call such an algorithm epsilon differentially private if the posterior probability that we can see here satisfies such a relationship between these two data sets that in which one of them exclude one specific user's data, like Bob's data. And obviously, the smaller epsilon is, the two posterior probability is going to be closer, and in that case, we have perfect indistinguishability or zero differential privacy. Unfortunately, differential privacy is a costly operation, and that requires a noise to be added to the outcome of different queries that have been asked by users from the server. So usually the way practitioners, the way that they approach it is they ask the query, and the query result is typically being perturbed by some class of noise like Laplacian noise or Gaussian noise, each of which satisfy one version of differential privacy. So in the case of Laplacian mechanism, we are interested basically in the epsilon differential privacy, which is the strongest notion. And in the case of Laplacian, we can basically go with a smaller, like weaker version, which is called epsilon delta privacy, differential privacy, which allows for a very negligible amount of privacy violation that is called delta or bad outcome probability. And each of the classes, noise will be basically related to the standard deviation of each of these classes of the noise. For example, in the case of Gaussian mechanism, we've got standard deviation that is a function of both epsilon and delta, and the difference that one individual can make in the output of the query, which is called the sensitivity, noted as delta in here. So with that being said, we now go to we now present some background on very important type of data called multimodal data, which can be seen in anywhere, and ranging from medical data to some robotic application, audio processing application, and mostly can be seen in also traffic analysis and vehicular studies. Fortunately, these types of data, when are seen from through the lens of privacy, have one important challenge that was not tackled to this work, and that is the fact that since we are dealing with a modular data, each data set could be in different modes. We need to provide privacy for both cases of modes and both measurements. So, for example, in the case of traffic monitoring, we have to provide privacy to both flow of the car on the street and the fact that whether the road is in the congestion mode or is it in the free flow traffic mode. That leads to an unnecessary randomization, as our work will shed light on it. So this solution, although has a broader scope, we instantiate the methodology around the very important task of traffic monitoring. So to shed light on that application, we are sticking to this very old school model for the traffic, which is called LWR model, or triangular fundamental diagram, where we are in free flow with a velocity constant VF, or congested flow in a velocity constant omega, which is much smaller than VF. And the two modes are separated when the density of the road over the road is approaching rho C, and the Q, of course, in that point is maximized flow of the car on the street. So the tool to collect information and facilitate this kind of analysis, at least before the era of GPS, was these single loop detectors, where they were collecting occupancy time and volume of the car passing by these single loop detectors, and they will account for documenting the portion of the 30 seconds, each 30 seconds that single loop detectors were activated, and the number of cars passing by. And with these two measurements of count and occupancy, with some other public parameter like B, which is the average effective vehicle length at the sensor location, which practically can vary from a compact car to a truck, we could roughly estimate the traffic and identify whether we identify the traffic monitoring that can be seen in such a traffic monitoring map as we show here. Our experiment is basically based on a very famous data set, which is a set of occupancy and count measurements that was collected in a day of highway I-80, and we basically tried to address the most challenging problem in this realm, which was basically how to reduce the amount of perturbation due to modes and measurement. So this work, as you see here, is a work that was published in 2015 in CCPS, where they provide privacy for both cases of counts and occupancy time to come up with such a map as you see on the right-hand side. Unfortunately, the solution shows that by taking such approaches, you need to make your differential private guarantee will be function of number of sensors over the road. So as the car passing by these loop detectors, are going to be more susceptible to attack. And at the end of the day, due to this parameter, like this case is 10 sensors, due to this additive parameter, the privacy will be completely compromised. So with that motivation, we proposed our methodology, which we basically divided the multimodal model to two zones, And we come up with this zone sensitive solution where one zone is not necessarily sensitive to add or remove one car, which is basically the coming from the definition of differential privacy. To make it more clear, if you are in the green zone, which is called safe zone, if one car is being added here or here, we don't expect that all of a sudden the traffic goes to the jam situation or congestion situation or vice versa. And with that being said, we only need to apply our perturbation for mode in the red zone, which is called the sensitive zone. So this work, if you look at, check out our paper, most of the theory and the reasoning that we provide and also the evaluation is to formalize these two regions and find the boundaries for the two regions and then driving the epsilon delta differential privacy. So here, as you see in here, we present our main methodology, which basically leverages the occupancy and count into the measurement. We've got Gaussian mechanism for the count and some private mode measurement model. And we enhance the utility of private mode measurement using some hidden Markovian model filter. And then we go with the LWR diagram, the triangle, which is now facilitates the zone version. And finally, using extended Kalman filter, we can drive this the evaluation. So this is the evaluation before applying differential privacy. As you see, our non-private map compared to the non-private map that does not have a sensitive or safe zone, only compromise those measurements that has very few number of cars on the road, which is basically like a free flow, and the most of the shape will be preserved. With the same analogy, we propose, we show that our solution can come up with remarkable results of logarithm 2 and 0.05 dp, which is considered as a very strong differential privacy and is independent of the number of sensors installed over the road, compared with the ICCPS 2014 work, which is basically a function of the number of sensing devices over the highway. As a concluding remark, we presented new methods for privacy preserving multimodal data analysis. And as we mentioned, this solution can have application in different realm of multimodality. And we instantiated the methodology using traffic monitoring application. And we showed that our sensitive zone solution significantly improved the privacy utility trade-off. And as a future direction, we are considering applications which require several modes, and we want to study how we can define those sensitive and safe modes in that context. Also, the one thing is really important, as we realized in the traffic monitoring case, was the dynamics and the DP mode measurements that are really important parameters that have to be taken into account in this methodology. And finally, the application of the solution can range from health data monitoring analysis, cloud computing, and safe networking. With that, I'm coming to the end of the presentation. I'll be happy to take any questions. Thank you very much.